If you haven't already, I'd like you to watch a video that I saved in this unit called Bowling Ball Motion Study. In that video, you see a ball being released by a robotic arm that has a spin as it first contacts the lane. So I want to do a slightly different study of the motion of a bowling ball in the case where the ball is just released straight down the lane of the bowling alley. So a picture for that is drawn here. You see an initial velocity, v naught, as the ball leaves the bowler's hand. And then there's the sliding phase. From point A to point B, there's a coefficient of kinetic friction. It's pretty small. In in the bowling alley that you go to, it's relatively higher coefficient of kinetic friction than it is for professional bowlers. That coefficient of kinetic friction gives a lot of control to the ball, and it makes this sliding phase shorter than it would be in professional competition. In any case, the ball slows down as it goes from point A to point B because the force of kinetic friction acts in the negative direction. So we'll say we have an x-axis and positive motion is to the right. So there's a force of friction in the negative direction, which brings the velocity of the center of mass from whatever its initial speed is down to some lower speed. And while all that's going on, the angular speed starts out at 0, not in the video that you watched, but in the example that I want to reference here. I want to imagine a case where the bowling ball has no spin when it first comes out of your hand, but that force of kinetic friction not only slows the ball down, but it provides a torque. See, that force of friction is actually acting here at the contact point. And so that provides a clockwise torque that brings the angular velocity from 0 up to some other final value. So let's consider the net force that's acting on the ball, as well as the net torque that's acting on the ball, in order to answer two questions. Number one, how does the speed of the center of mass when it reaches point B compare to the initial speed when it's released at point A? Secondly, how much time does it take to make that change in speed as it travels from point A to point B? So the net force is illustrated with a free body diagram. Normal force points up, mg points down, and then there's that force of kinetic friction back to the left, and the force of kinetic friction is equal to mu times n. We can put mu k, just to remind us that this is the sliding phase of motion. So in the sliding phase, just to be clear, this contact point has relative velocity compared to the ground that it's on. But from point B onward, now the ball has gripped the lane, so to speak, and from there on, you get pure rolling motion, or rolling without slipping. And in that case, the velocity of the center of mass is equal to the angular velocity times the radius of the bowling ball. Okay, so from this free body diagram, it looks like the net force is equal to, careful, using our frame of reference, the net force would be negative mu kinetic times normal force, but then again, normal force and mg are equal. So I'm going to say the net force is negative mu mg. So mass times acceleration is negative mu mg. We cancel out the m. And the acceleration as the ball moves from point A to point B is just equal to negative mu times g. So let's put that information on hold and make an investigation of net torque. Okay, so the net torque, we should probably make a rigid body diagram. The force of friction is acting at the contact point. That's equal to mu mg. And let's consider the center of mass to be our axis of rotation. That means if a bowling ball is modeled as a solid sphere, the rotational of inertia is 2/5 mr squared, and the friction force is acting with a lever arm of capital R and acting at an angle of 90 degrees relative to the force. So our net torque is equal to a force of mu mg acting with a lever arm of R, and I'll go ahead and write in sine of 90 degrees, but then again we know that's just equal to 1. We replace net torque with I alpha, so in the end that gives us I alpha equals mu mgr, so 2/5 mr squared alpha equals mu mg times r. Let's cancel out the m, and let's cancel out one of the powers of r. So we get alpha times r is equal to 5/2 mu g, or alpha is equal to 5 mu g over 2r. Now let's do some kinematics. We have an expression for the angular acceleration, and we also have, if I can copy down below, an expression for the linear acceleration. So the acceleration of the center of mass is equal to negative mu g. There's our linear acceleration measured in meters per second squared versus our angular acceleration measured in radians per second squared. So let's look at the translational kinematics, and then side by side the rotational kinematics. Translation versus rotation. So there's an equation that tells us that final speed equals initial speed plus acceleration times time. In the same vein, another rotational kinematics equation says final angular velocity equals initial angular velocity plus angular acceleration times time. So we have a final angular velocity that's equal to, so in our case, we're imagining the bowling ball coming out of our hand, strictly sliding without any initial rotation. So omega naught is 0. So we get omega is equal to alpha t, but alpha is 5 mu g over 2r. So we have 5 mu g t divided by 2r as the final angular speed. Now let's look at the change in linear speed. V equals v naught plus at, but a is negative mu g, so v equals v naught minus mu g t. And this is an equation to tell us the motion of the center of mass of the bowling ball. Now here's the key to this. From point A to point B, sliding occurs, but once the bowling ball reaches point B, then the rest of its journey down the lane, all the way until it collides with the pins, forgive me for these sloppy looking pins, is pure rolling motion where the velocity of the center of mass is equal to whatever angular speed it has multiplied by the radius. So I can make that substitution, right? We can say that VCM also has to equal omega times r. So we make a substitution. So we have one equation for the velocity of center of mass and another one that have to agree with each other. So the velocity of the center of mass is equal to, well, if I multiplied 5 mu gt over 2r as omega and then multiplied it by r, that just makes the r cancel out. So we find the velocity of the center of mass has to be 5 mu gt divided by 2. So if that's the case, we have 5 mu gt divided by 2 equals v naught minus mu gt. So we'll add mu gt to both sides of the equation. So 5 halves plus 2 halves, what would that give us? V naught is equal to 7 halves mu gt, which is the same as saying t is equal to, undo that, t is equal to 2 v naught divided by 7 mu g. So think about what that tells us. The amount of time it's going to take to go from point A, where it just comes out of your hand, sliding down the lane, until it reaches point B, when it finally achieves a state of pure rolling motion. The time to make that change is equal to 2 v naught divided by 7 mu g. Meaning, as v naught goes up, the time it takes to reach a state of pure rolling motion also goes up. And that makes sense. The faster it comes out of your hand, the more time it's going to spend in its sliding phase. Likewise, this equation tells us as the coefficient of kinetic friction goes up, the time goes down. So the more roughly waxed, so to speak, the lane is, the less time it'll take to reach that state of pure rolling motion. Anyway, if we know the time it takes, then we can say the final speed of the center of mass is equal to the initial speed, however fast it comes out of your hand, minus mu gt, just copying the equation from above. But now we know what t is equal to, so we make the substitution, and the velocity of the center of mass is v naught minus mu g times 2 v naught over 7 mu g. So I find this interesting that not only does the g cancel out, but so does mu. So we end up with an expression that the velocity of center of mass by the time you've reached point B down the lane is the initial speed minus 2/7 of the initial speed. So we can think of this as 7/7. So the final speed, once it finally reaches a state of pure rolling motion, will be equal to 5/7 of the initial speed. And notice that that's independent of the value of mu. Isn't that curious? So no matter whether you're a professional bowler or a weekend warrior, whatever the coefficient of kinetic friction happens to be, once the bowling ball reaches a state of pure rolling motion, the speed of the center of mass will always be 5/7 the speed at which it came out of your hand. Okay? Now, the time it takes to do that will vary with mu. But no matter what, the final outcome in terms of the speed is always the same. So there's an interesting problem on the motion of a bowling ball, and if you need to, go back, review those steps, and see if you can derive this same expression on your own.